Hi, I'm Herb Gross, and welcome to lecture number 37 in our series Gateways to Algebra, where today we're going to do one of my favorite topics. It's a very exciting topic that to me goes far beyond algebra. It's going to be called extending the number system. But what it really deals with is that as you progress in any kind of a society, whether it's the technological society, the sociological society, doesn't make any difference. Things go along quite smoothly, and all of a sudden you come to a crossroads where either you have to invent something brand new or become stagnant at the level that you're at. And so basically what happens is we go up to a certain point, discover that we need something new. And when we discover that something new, we get a whole new horizon compared to what we had before. But from that new vantage point, we then stumble into problems that we couldn't even see from where we were before. And what's happening today is we have now defined something called the real numbers, and it's going to turn out that to go beyond this, we're going to have to invent something else. And that's where the title, Extending the Number System, comes from. But let me begin by way of a review. Let's suppose that we assume that people look for the simplest solution that plagues them. And they look only for a more complicated solution when the simplest solution either becomes too cumbersome or else doesn't work. The first numbers that people used were the numbers used for counting, 1, 2, 3, etc. And we'll throw in 0, assuming that place value was invented. And these are called the whole numbers, which I'm calling the first number system. You see N for number system and the subscript 1 for the first number system. So based on this number system, suppose I write down the equation x plus 2 equals 3, which in the language of sets says the set of all x for which x plus 2 equals 3. Well, in this arithmetic system, we see that x equals 1 is an answer. And so what we say is the solution set is 1. And notice that we know what the number 1 is because it's a member of this set. Now suppose I say I want the set of all x such that x plus 3 equals 2. Now, this equation makes sense because the numbers 2 and 3 are in my set n sub 1. The problem is, since all of these numbers are non-negative, anytime I add something onto 3, I'm going to get something bigger than 3, or at least as big as 3. So it's impossible within the set n1 to find the solution to the equation x plus 3 equals 2. In other words, the solution set is empty. However, now I'm at a crossroads. I can either say, hey, we can solve this equation, or I have to say, let's invent a new number system. Now, what way should I go in this? If I can't find any reason for having a solution to this equation, I'll just drop it. But isn't it possible on a particular day that it was so cold that after the temperature warmed up by 3 degrees Fahrenheit, it was still only 2 degrees above 0 on the Fahrenheit scale? In other words, is it possible that there was some temperature such that when you added 3 degrees onto it, it was still only 2 degrees? And our experience tells us that the thermometer scale can go below 0. So what we now do is we don't invent a new number system. What we do, only we use a more technical term. We extend the number system to include a whole type of new thing. For example, in this case, we now invent a new number system, and we'll call this what? The second number system, n sub 2. And we keep the 0, but now instead of 1, 2, 3, we're going to have what? Positive 1, positive 2, negative 1, negative 2, etc. See, all we've done is we've done what? We've augmented this collection to include the negative integers as well as the 0 and positive integers. Now look what happens. Now we can solve the equation x plus 3 equals 2. Namely, x would now be negative 1, and we've solved the equation. By the way, look what's happened to the previous equation that we solved, the set of all x such that x plus 2 equals 3. We were able to solve that problem before, and we said that the solution was 1, x equals 1. However, notice in this set, there is no 1. There's a positive 1, there's a negative 1, and the solution here is what? Positive 1, which means that when we extended this system, the names of the previous members had to change. In other words, 1 and positive 1 are going to mean the same thing. Let me see if I can illustrate this for you in a more general situation. Suppose I have any set A, and there's a whole bunch of things that belong to A. Now I extend the set A to include a larger collection B. Now look what happens. Every member in A also is inside B, isn't it? So what happens is, if I call this element here little a has dual citizenship. It belongs to both capital A and to capital B. Therefore, if I make up a rule of arithmetic in A, and I also make up a rule of arithmetic in B, I have to make sure that whatever new name A has in the bigger society, that the rules of combination stay the same. You see, in other words, you don't want to have two different answers, one of which is based on if you view A as being in this circle, and the other of which is based on seeing A in this circle. We have to have consistency. So let me just go a little bit further and show you what I mean by that. See, now we have this new set, the second set of numbers that includes 0, positive and negative 1, positive negative 2, positive negative 3, and so forth. Now I write down a new set. I say the set of all x such that twice x is equal to 1. Well, look at, there's no number in n sub 2 that can possibly work. Why? Because when you multiply any integer, positive, 0, or negative, by 2, the answer is going to be an even number. But 1 is odd. And since an even number can't equal an odd number, there is no such number. So the answer is 0, the empty set. Now, the real problem is there a time when you want to be able to solve this equation? Well, for example, suppose you bought, say, 2 candy bars for $1. It makes sense to say what was the price of each candy bar. You see, there is a number that's not a whole number of dollars that expresses how much each candy bar costs. So since we want there to be an answer to this, we now have to make up a new notation. Going back to basic arithmetic, the fraction a over b is actually a simplified version of saying what? The set of all x such that when you multiply x by b, the answer is a. In other words, what is 1/2? 1/2 is a set of all numbers such that when you multiply it by 2, you get 1. There is only one such number, and that's the number that we call a half. Now look what happens. Let's look at the number 6 over 1 this way. According to this definition, what does 6 over 1 mean? 6 over 1 means what? The number you must multiply by 1 to get 6. Well, that number is already called 6. So on the one hand, in the extended form, the name is 6. In the original form, in the extended form, the name is 6 over 1. In the original form, the name is 6. So therefore, 6 over 1 and 6 must be different names for the same item. And do you see what's happening so far? What's happening is we go along our own merry way, things go great, and there's something metaphysical that happens. When you write down an equation that makes sense, it's conceivable that to solve that equation, you're going to have to invent something that you don't already have. See, in other words, you can understand the equation x plus 3 equals 2 if you've never heard of negative numbers, but you can't solve it unless you know negative numbers. You can understand the equation 2x equals 1 if all you've heard of is whole numbers, but to solve it, you're going to have to invent the rational numbers. And in this spirit, we just kept on going and going and going, okay, until we got to the stage where we define something called the real numbers. I won't call this anymore. R will stand for the real numbers. Now, there's no significance to the meaning of the word real other than reality is in the eyes of the beholder. See, we define the real numbers to be what? The set of all numbers x for which x squared is non-negative. In other words, we'll explain that in a minute. In other words, x is real if its square is greater than or equal to 0. Now, based on that, let's write down the equation, the set of all x such that x squared plus 1 equals 0. That equation makes sense. The problem is, to be a real number, x squared has to be at least as big as 0. Now, if x squared is at least as big as 0, adding 1 onto it makes the answer at least as big as 1. So hence, as long as x is a real number, there is no solution to the equation x squared plus 1 equals 0. Hence, the solution set is empty. Now, where did the real number image come from? Geometrically, R is simply the number line, the x-axis. See, what does the x-axis get made up of? There's a 0. Everything to the right is positive. Everything to the left is negative. 0 times 0 is 0. Negative times negative is positive. Positive times positive is positive. So any number that can be represented as a point on the x-axis, on a number line, is going to be a real number. Now, it doesn't say that other numbers don't exist. In other words, I could have picked a point up here someplace. All we're saying is that if I have to extend the number line to include more, That's the only way I'm going to find the solution to this equation. Let me just word that slightly differently. If I don't extend this number line to include more numbers, then the equation x squared plus 1 equals 0 will never have solutions. Now, the real question to ask is, are we ever going to need to solve the equation x squared plus 1 equals 0? I will try to show you in the not too distant future that there actually are applications to knowing a number whose square is negative. But that's not the real crucial issue, because even if you didn't know, could you out of intellectual curiosity say, let's just pursue this a little bit further? So let's see what we could have done over here. Here's this real number line. That's only a small part of this page. Why can't I do the same thing that Descartes, remember the fellow who was responsible for giving us coordinate geometry in the first place, and this is called the Cartesian plane. See, instead of taking one number line, let's take another number line perpendicular to the first number line, and now what we say is, look, can't we name any, see, why is this point P any less a first-class citizen in the plane by being up here rather than by being down here? After all, if I had put the x-axis over here, then P would have been a perfectly good real number, and all these numbers down here wouldn't have been. So what we do is the following. We say, okay, let's start naming points in the plane of the paper. What we'll do is take a point, but now you see we need two dimensions. If all I tell you what the x value is, see, suppose I say x is a, so I move a units out, and if x is a, I could be any place on this line. But if I also tell you what the height is, what the b value is, then I know what? If the y value is b, then I have to be where? Any place on this line. And to be on both lines at the same time, I must be where these lines meet. So we've done this before with our coordinate geometry when we did graphing, but you see what's happening now? In the same way that I could name every point on the x-axis by a single letter, I can now name every point in the plane by a pair of numbers. And by the way, notice what happens. Every point on the x-axis now gets a new name. You see, this point over here is no longer called A, it's called what? A, comma, 0, because it tells me what? That the horizontal displacement is A, but that the vertical displacement is 0, meaning it puts me right on this line. Now, this causes some very significant changes in how we look at geometry. In the real world, notice I put real in quotation marks here, when we were dealing with real numbers, see, that means we're on the x-axis. If the absolute value of the number that goes from O to P is 2, then what that told us was what? P had to be 2 units from O, 0. The only way P could be 2 units from O, since P had to be on the number line, is it could either be where? 2 units to the right of 0, in which case it would be called positive 2, or else it had to be where? 2 units to the left of 0, in which case it would be called negative 2. In other words, if the absolute value of O to P was equal to 2, then the name of the number that P represented was either positive 2 or negative 2. But look what happens in the new world. Now if we say the distance from O to P is 2, look what this means. All it means is we can now roam through this whole plane. So starting at O, I can just mark off 2 in any direction. See, from here to here is 2, from here to here is 2, from here to here is 2, and I haven't drawn it in, but can you see the circle being formed here? See, what have I done here? I can draw a circle centered at 0 with radius equal to 2, and every point on that circle will be 2 units from O. So all of these points satisfy this relationship. And that brings us to something called a vector, a quantity that requires both a magnitude and a direction is called a vector. In this sense, signed numbers are actually vectors, because when I say go 3 units, I have to tell you whether I mean 3 to the right or whether I mean 3 to the left. Now, not everything is a vector. For example, suppose I tell you that I walked for 2 hours. Where I finish does depend on the direction I took, but how long I walked doesn't. See, a scalar is a number that doesn't depend on direction. See, the scalar is just, see, when we're talking here, it's not just knowing how far you walked, you have to know what? In what direction did I walk? And by the way, we have worked with this before with signed numbers. When we said that 3 plus 2 is 5, what we said was if you start at O and go 3 units to the right, see the arrowhead here? that indicates I'm going to the right. And now I go 2 more units to the right. See what I've done? The second arrow, the tail starts at the head of the first. And what did I do now? I measured the distance of the direction, the vector, so to speak, that started at the tail of the first one and ended at the head of the second one. So the vector, the sum, positive 3 plus positive 2, is the vector that starts at 0 and proceeds over to the point Q over here. Now let's re-examine 3 plus negative 2. See, positive 3 means what? You went 3 units to the right, so I draw the arrow this way. Negative 2 means you came back 2 units to the left. Technically speaking, this second line over here should be on top of the black line, but so that you can see it better, I've lifted it up a little bit. So now we do what? Why is the answer here positive 1? And the answer is that when you go from the tail of the first to the head of the second, you've moved 1 unit to the right. Well, now you see the point is, since we're already adding vectors when they're real this way, we're going to extend that definition to the case where the vectors aren't all along the x-axis. See, now suppose you have any directed length starting at 0 and going to some point P in the plane. We'll call that vector A. Now suppose at the head of P, I put down another vector B that terminates at the point Q. See what's happened? The second vector starts at the head of the first vector. Now I draw the vector, the line, that starts at the tail of the first and goes to the head of the second. See that vector? That's called the vector sum. That's how we're going to add 2 vectors. And to give this a little bit more life, let me show you what this looks like in terms of a diagram. Suppose P sub 1 is the point 3 comma 1. And suppose P sub 2 is the point 2 comma 5. See, 3 over, 1 up, 2 over, 5 up. Okay? I want to add these 2 vectors. Well, the first one is over here. What do I do now? I take the second vector and move it without changing its size or its direction so that its tail coincides with the head of the first. Then the sum is going to be what? The vector that goes from the tail of the first, from 0 to the head up here, and what's that number going to be? Well, look at, from here to here is 3. From here to here is 2. See? And so the 2 over here, you see what's happening? I go 3 plus 2 more. That makes the x-coordinate 5. What's the y-coordinate up here? Well, what's happened over here? This is already 1 unit up, isn't it? This vector here is 5 units long, so 1 plus 5 is 6. So writing this thing symbolically, 2 comma 5 plus 3 comma 1 is 5 comma 6. Okay? And by the way, notice what happens over here. We added the 2 first numbers and we added the 2 second numbers. We want to find a way of writing this differently because we don't like the parentheses in math. So what we do is something like this. In the same way that the arrow 1 is the vector that does what? It goes along the positive x-axis 1 unit long. We take its companion, the vector that's 1 unit long, going in the positive y direction, and we just call that vector I. So what we say is a new notation is going to be that the arrow that we would have called 2 comma 3 is now going to be called 2 plus 3i. In other words, the component in this direction will always be indicated by multiplying the I. See, technically, this is really what? The 2 multiplies the 1, and the 3 multiplies the I. So you have twice this unit and 3 times this unit. So now what happens when we do that, the 2 comma 5 plus 3 comma 1 equals 5 comma 6. Look what happens over here. 2 comma 5 means 2 plus 5i, and 3 comma 1 means 3 plus 1i. But we already have rules for arithmetic. In this extended number system, we want those rules to be the same. So we're still going to adopt what? The commutative property, the associate property. Isn't 2 plus 3 5 whenever 2 and 3 modify the same noun? Isn't 5 plus 1 6 whenever 5 and 1 modify the same noun? So what I'm going to do is I'm going to group all the terms that don't have an I in them together and all the groups that do have an I in them together. So I rewrite this as what? 2 plus 3 plus 5i plus 1i. That gives me 5 plus 6i. And by the way, just to emphasize what's happening in this extended number system, look what's happening. The number that we used to call 2, see, where was that number? It's over here. How do you name that? It's 2 in the one direction and 0 in the I direction, so it still has the form what? 2 plus 0I. A real number plus a real number times I. See, it's 2 comma 0. The number I really is what? It's 0 in the real direction, 1 in the I direction, so it's 0 plus 1I, and that's called what? 0 comma 1. You sort of get the idea this way? Now, after having done all of this theory, the real question is, why would you have vector addition in the first place? Well, let's take a look at an example. It's a fairly simple example. Suppose I'm in a boat, and I'm starting at this point S, and I want to ride the boat, drive the boat, directly across the river to point F. And I'm driving at 10 miles per hour, and I point the boat in the direction of where I'm going. If I'm not careful, I might not notice that there's a 5-mile-per-hour current flowing perpendicular to my path of motion. In other words, if this is south to north, this is an east to west current. What's happening as I'm driving the boat? I've got the boat pointed this way, but the current is pushing it like this. So that even though it looks like I'm moving straight ahead, in reality I'm moving like this. I'm drifting, as the expression goes. You see, to find out what my true velocity is, in other words, how fast am I going and in what direction, I draw a line to scale in this direction 10 units long, in this direction 5 units long, and the vector that goes from the tail of the first to the head of the second is my velocity vector. You see, in the real world, this is how I'm adding two lengths. Same thing happens when you talk about a headwind and a tailwind. See, when an airplane is flying, a tailwind means that there's a wind blowing exactly in the same direction as the plane. A headwind means the same wind, but it's blowing against the plane. So when you're traveling with the wind, if p is the speed of the plane and w is the speed of the wind, with the wind, the speed is p plus w. Against the wind, it's p minus w. And in fact, a very simple algebra problem is based on the fact that if you know how far and how long it took to travel a certain distance with the wind, and how far and how long it took to travel a certain distance against the wind, you can find out both the plane speed and the wind speed. For example, suppose with the wind, the plane goes 2,400 miles in 4 hours. Okay? That means that each hour the plane went 600 miles, and with the wind means you add these together. So p plus w is 600. Now against the wind, what happened? 5 goes into 2,500 500 times, so you traveled 500 miles, but against the wind means what? You're subtracting the wind speed from the plane speed, so that would be 500. Now if p plus w is 600 and p minus w is 500, we've already learned how to solve that. We simply add these two equations, the w's cancel, 2p is 1100, so p is 550, and once p is 550, it's easy to see that w is 50. But the point I wanted to make is that with our new extended number system, we are no longer restricted to headwinds and to tailwinds. For example, suppose this vector represents the speed of the plane, and w still represents the speed of the wind, the velocity of the wind. The wind can be moving at a certain speed in any given direction. And hence, to find out what your speed is relative to the ground, you would have to do what? Depending on what the wind speed was, draw the vector that started at O and terminated wherever you were interested in looking at. Notice that the fastest you could be going is when you're going with the wind. The slowest you could be going is when you're going against the wind, but that any one of these intermediary positions is now possible. See, for example, suppose this represents the wind over here. What I have to do is what? Just draw this particular vector. Now, we're coming close to the end of today's lesson, so let me stop by showing you the one thing that's left to do. We've been talking about addition so far. What if you wanted to multiply two vectors? For example, we've already talked about the vectors I and 1, so why not concentrate on those? What would happen if I multiplied I times 1? I times 1, which by the commutative property of multiplication, because we're extending the number system, would still have to be the same as 1 times I. But what does 1 mean? 1 means, in the real number system, the number that doesn't change anything when you multiply by it. So if we want 1 to still have that property, 1 times I would have to equal I. Well, look what happens. Here's 1, here's I. What seems to have happened when we multiplied 1 by I? We didn't change the magnitude of the vector, but somehow the angle changed. In other words, instead of being horizontal to the right, it's now vertically upward. And what this does is it seems to indicate, we're going to investigate it further in the next lecture, but for now, it seems to indicate that multiplying vectors in the sense that preserves the real number structure is going to require that we not only multiply the magnitudes, but somehow we're going to have to work with those angles. And how that's going to work, we'll see soon. But before we do that, since we're going to be talking about angles, I should have an enrichment lecture coming up on what we mean by angles and directions, and that is exactly what we're going to do next. The next lecture will be based on measuring angles, but until next time, have fun, study hard, stay young. See you next time.